Good day everyone, we are Group 4. Today we will be presenting about Boolean algebra, a fundamental concept that connects mathematics, logic, and computer science. Let's get started. Boolean algebra is a specialized area of mathematics that deals with variables having only two possible values, true or false, or in binary terms, 1 and 0. It provides a formal framework for reasoning about logic and binary systems, which are the building blocks of digital electronics and computing. This system was introduced by George Boole, an English mathematician and logician, in 1854 through his work An Investigation of the Laws of Thought. Boole's idea paved the way for symbolic logic and the logic we now use in computer programming and digital circuit design. In Boolean algebra, instead of using arithmetic operations like addition and multiplication, we use logical operations such as AND, OR, and NOT. These operations follows specific rules that help simplify complex logical expressions and make digital circuits easier to design and understand. Now, let's take a closer look at the main Boolean operators. First, AND returns true only if both inputs are true. OR returns true if at least one input is true. NOT reverses the value if it's true, it becomes false and vice versa. XOR or exclusive OR returns true only if the inputs are different. Not AND, the opposite of AND. It returns true unless both are true. Not OR, the opposite of OR. It returns true only if both are false. These logical operators are essential in computer science because they form the foundation of logic gates, which are used in computer circuits, processors, and even everyday technologies like smartphones and calculators.
When you try to drive the e-bike without a battery, it doesn't work. That means one condition is false. When you add the battery but don't turn on the power, it still doesn't work. Another false condition. But when the battery is inserted and the power is turned on, the e-bike finally moves. And that's how AND logic works. Both conditions must be true for the output to be true.
Today, let's talk about the Boolean algebra operator OR. So, in Boolean logic, OR is one of the basic operators we use to make decisions. So, if at least one conditions are true, then the output will also be true. The only time OR gives a false result is when all conditions are false. So, now, how do we apply this in real life scenarios? So, think about the simple decisions. Should we bring an umbrella? Conditions are, is it raining or is it cloudy? So if it's raining, we bring 1, and if it's cloudy, we still bring 1 just in case. So the only time we don't bring an umbrella if it's neither raining nor cloudy. We also use OR every day in technology. So for example, logging into your phone, so you can unlock it with your password or with your fingerprint. So in both cases, if one method works, then you can get access into it. So, in medicine, OR logic is applied. For instance, a doctor might say, we'll give you a treatment if you have a fever or shows of infections. So, in that way, action is taken as soon as one conditions or one warning signs appear. So, in short, Boolean operator OR is about flexibility. It allows us to proceed when there are possible conditions to check. So in computing, it helps machines to make quick decisions. In everyday life, it helps us handle uncertainty and choose wisely.
Let's talk about negation logic, also known as the word not. Negation simply flips the truth of a statement. For example, here's my statement: the light is on. Now, if we apply negation, we get the light is not on. That's it, we just reverse the meaning. In logic, this isn't just words, it's about truth values. Here's how it works in a truth table. If the light is on, the statement "the light is on" is true, and its negation "the light is not on" is false. If the light is off, the statement "the light is on" is false, and the negation is true. In math symbols, if we let P represent "the light is on," then not P, written as negation P, means the light is not on. So every time you switch a light on or off, you're actually demonstrating logical negation in real life.
Imagine you have a two-way light switch. The switch from below is on and the other switch is off. You want to turn the light on from the above. When you flick the switch on, the light turned on. Put it in the table. Let's say the variable A is the switch 1 and variable B is switch 2. A XOR B is the state of light bulb if it's on or off. If both switch 1 and switch 2 are turned off, then the light bulb will also off. Switch 1 is off and switch 2 is 1, then the light bulb is on. Same thing in XOR operator. That's how it works. If two switch are different, then the light bulb will only toggle if the value is different from the other. But if switch 1 and switch 2 are both on, then the light bulb will still turn off. So that's how the XOR logic works in real life. So a two-way light switch is a physical implementation of the XOR logic, allowing two switches to control one light in a way that toggling either switch always changes the state of the light.
So today I'm gonna talk about the NAND logic or the NOT AND logic of Boolean algebra. So NAND logic or the NOT AND logic is basically the opposite of AND logic in Boolean algebra. If in AND logic, in order to get a true output, the two conditions must be true. In NOT AND logic, the output is always true unless the both conditions were true. So imagine using a laptop where it automatically turns on its fan when laptop is busy and the laptop is high temperature. So let's take a look in this truth table where the first condition is laptop is not busy and the second condition is laptop is cool. So if the first condition is false and the second condition is false as well, then the NOT and output will going to be 1 since the laptop is busy and laptop is in high temperature. In this truth table, our first NAND output will going to be 1 or fan is on since our first condition is false, meaning the laptop is busy, and our second condition is false as well, meaning the laptop is in high temperature. Our laptop will automatically turns on its fan. And for our second NAND output, it is still 1 or fan is on since even though our laptop is cool, it is still busy and still need the fan. And in the third output is still true or 1, fan is on. Even though our laptop is not busy, it is in high temperature and the laptop still needs the fan. And if both conditions are true, meaning the laptop is not busy and the laptop is cool, our laptop will going to turn off its fan, so meaning the NAND output will going to be 0.
I'll be sharing how discrete mathematics, specifically the NOR operations, plays a role in something very familiar to us, the social media notification. When we scroll through Facebook, TikTok or YouTube, the posts and alerts which we see are not random. They are carefully chosen by algorithms built on logic operation like NOR. The NOR operation stands for not or. Its true or 1 only if both inputs are false or 0. Let's look at the truth table. If A is equal to 0 and B is equal to 0, the NOR gives 1. In all other cases, NOR gives 0. Now, how does this apply to social media? Let's assign our inputs. In A, did you interact with a post? In B, did you recently view similar posts? The system applies NOR logic if both are no. The output is 1, meaning the platform sends you a notification about new content to keep your feed fresh. But if you interacted or already saw similar posts, the input is 0, so you won't be notified about the same type of content again. For example, if I didn't like, share, or comment on sports video and I also haven't viewed similar ones, then both inputs are 0. The NOR operation gives 1, so my feed might suggest cooking or travel videos instead. This prevents repetition and introduces variety. In conclusion, the NOR operation is not just a logic gate in theory. It has real application in the digital world, like filtering social media notifications. It ensures that we don't keep seeing the same content, but instead we discover fresh and engaging posts. This is one of many ways discrete mathematics shapes our everyday technology.
In summary, Boolean algebra is not just a branch of math. It's the language of modern computing. From simple logic problems to complex digital systems, it helps us understand how decisions and operations are made in the digital world.